Welcome back to The Explainer. Today we're taking a massive cosmic road trip. We're going from our own familiar cosmic backyard right out into the deepest, darkest molecular clouds of the universe to hunt for alien life. And we're using some truly revolutionary tools, like the James Webb Space Telescope, to piece this giant puzzle together. You know, for decades we've basically been waiting around for a radio signal to say hello from the stars. But what if the first true, undeniable signs of extraterrestrial life aren't found in a broadcast, but in a weather report? That's the mystery we're unpacking today. How tracking planetary atmospheres and complex chemistry is currently our absolute best shot at finding biology out there in the dark. Here's how we're breaking it down today. First, secrets of our solar system. Second, unlocking distant exoplanet atmospheres. Third, a new recipe for life. And finally, the cosmic building blocks. All right, part 1. Secrets of our solar system. Before we can even begin to understand distant worlds, we really have to look at our own familiar neighbors, because they still hold some incredibly massive mysteries. Take Jupiter's icy moon Europa. Back in 2014, these famous Hubble Space Telescope observations suggested that giant water vapor plumes were erupting straight from its surface. I mean, it was incredibly exciting, right? A potential direct window into a subsurface ocean, but a recent study from the Southwest Research Institute threw a bit of a wrench into that. After reviewing 14 years of data, they cast some serious doubt on those plumes. They argue that those observations could actually be explained by other things entirely, like charged particle interactions, or even just data processing effects. So are the plumes really there? Well, NASA's Europa Clipper launched in 2024, and when it arrives in the Jovian system in 2030, we're finally going to get a definitive answer. The mystery deepens even further when we look at our ice giants. On September 21st, 2022, the James Webb Space Telescope turned its golden mirrors toward Neptune. And get this, in less than 2 hours of observation time, it pierced right through the planet's methane atmosphere to reveal impossibly crisp details. JWST clearly resolved Neptune's clumpy rings, the Galley, Leverrier, and Lassell rings. And it even spotted embedded moons like Despina and Galatea that are actively helping shape those rings. Down in the atmosphere itself, it saw a south polar feature so bright at 3 microns that it literally saturated the detector. It also revealed this warm equatorial band, which tells us there's a huge global circulation pattern where gas is actively sinking and warming right at the equator. Let's swing over to Saturn's moon Titan, because we have another incredible discovery there. JWST, teaming up with a Keck 2 telescope, observed Titan's 45-kilometer-high methane clouds in 2022 and 2023, and they detected something completely new, the methyl radical, or CH3. Now, this is an unstable compound that forms when methane breaks down. The crucial point here is that detecting this radical proved there is a highly active, rich, cryogenic organic chemistry happening right now in Titan's atmosphere. It is a vital intermediate step in making much more complex molecules. NASA's Dragonfly octocopter mission is literally going to fly through these very skies in 2034 to investigate this up close. Moving right along to part 2, unlocking distant exoplanet atmospheres. So, we've seen how dynamic our local solar system is. Now let's shift our focus far beyond our sun, out to the exoplanets. Take WASP-39b, for example. It's a hot gas giant. JWST analyzed it as part of the director's discretionary early release science program. And this brilliantly illustrates the entire point of this program. The goal is to swiftly characterize these warm exoplanetary atmospheres and release the data to the public immediately. By doing this, astronomers all over the world are actively learning how to filter out cosmic noise and actually decode the complex signatures of alien atmospheres. And honestly, decoding that noise is the biggest challenge we face. When we look at small, rocky planets in the habitable zone, like the ones in the TRAPPIST-1 system, the host star itself totally gets in the way. M-dwarf stars have super messy, heterogeneous surfaces. We're talking star spots, flares, the whole shebang. And that creates signal variations much larger than the tiny, faint signal of a planet's atmosphere. So how do we fix it? Well, Natalie Allen's team at Johns Hopkins University proposed a brilliant problem-solving trick. Using 128 hours of JWST time, they plan to observe 15 close transits of the inner, likely atmosphereless planet TRAPPIST-1b, along with the habitable zone planet TRAPPIST-1e. By taking the data from E and essentially dividing it by the data from B, they use the inner planet as a filter to mathematically erase the star's messy surface contamination. It leaves behind only the pure atmospheric signature of the habitable world. It is just incredibly clever. Alright, on to part 3, a new recipe for life. Okay, so once we have these brilliant tools to strip away the noise and look directly at an alien atmosphere, what chemical signatures are we actually looking for? It turns out the classic search for just oxygen might not be our best bet. A University of Washington study led by Joshua Christensen Totten pointed out that Earth hasn't actually had high levels of oxygen for most of its history. Instead, they identified a completely different atmospheric disequilibrium, basically a chemical imbalance that screams life. You need abundant methane, carbon dioxide, and liquid water, but crucially, a complete absence of carbon monoxide. See, methane and carbon dioxide represent extreme opposite levels of oxidation. It's really hard for non-biological processes, like volcanoes, to produce both of those without also belching out a massive amount of carbon monoxide right in the middle. UW professor David Catling perfectly summarizes why this matters. He says, "What's exciting is that our suggestion is doable. To understand why, you kind of have to think of carbon monoxide as a free all-you-can-eat buffet for biology. Microbes readily eat this stuff. So if you find a planet with methane and carbon dioxide, but the carbon monoxide is completely missing, it heavily implies there's a massive biological population of microbes just eating it all up. It creates a highly practical, compelling, and most importantly, an observable checklist for our telescopes. And that brings us to part 4, the cosmic building blocks. We've talked about how we track the weather, how we filter out starlight, and the specific recipe we need to find biology. But where do the ingredients for this recipe actually come from? Let's zoom way out to the freezing depths of interstellar space, long before stars and planets even form. The JWST Ice Age Early Release Science Program peered into dense molecular clouds. These are the dark, cold nurseries where stars are born, and they detected a remarkably rich inventory of volatile molecular ices along 2 pre-stellar lines of sight. They found isotopes of carbon dioxide and carbon monoxide, along with OCN, OCS, and, incredibly, the functional groups of complex organic molecules. This proves definitively that simple and complex molecules are forming very early in a water-ice-rich environment, way before planets ever take shape. To put that into perspective, the study revealed a massive contribution from these ices. These dense molecular clouds contribute between 2% and 19% of the total bulk budgets for key elements like carbon, oxygen, nitrogen, and sulfur. Those are the exact ingredients required for that atmospheric disequilibrium we just talked about. The universe is literally pre-packaging the chemical recipe to build habitable worlds before the star system even ignites. How cool is that? We have covered immense ground in this explainer today. From the cloudy, organic-rich skies of Titan to the clever stellar filtering of TRAPPIST-1, all the way down to the icy nurseries of deep space. And it really leaves us with one massive question to ponder. Will the James Webb Space Telescope, peering across light years to analyze distant exoplanet atmospheres, find it first? Or will the Europa Clipper, tasting the icy waters right here in our own solar system, be the first to definitively check the boxes of this new recipe for life? We have the tools, we finally have the recipe, and the search is officially on. Thanks so much for diving into this explainer with me, and keep your eyes on the stars. Subscribe to the Astrobiology Lab and follow for more.